Hello, everybody. Okay, this is kind of a primer and a refresher on some math that you probably knew at one time, but may not know anymore, or you may have forgotten, and that is okay. All right, y'all. We have here just kind of a selection of some of the relevant, I guess it's all relevant, but some of the FSE practice problems that you guys have access to, and hopefully will just jog your memory for some of the things that we will use in the course, even though this is just kind of that math in the abstract. We usually, mostly just have algebra in this course, and so this fundamental skills exam is what FSE stands for. You're going to take that exam in the course, early in the course, and it's just to kind of force you to go back over and remember some of the math that you probably once knew, but it's probably a little rusty. All right, so here we go. And we put together a kind of a practice set of problems that helps refresh on, some trigonometry and dimensional analysis and natural logs. And so that's essentially what this is. All right, let's press. All right, given this equation here, all right, this is a dimensional analysis problem. V equals 2 times square root of mu over r plus epsilon. Well, you will learn about this equation, but you just don't know it yet, and that's okay. You don't need to know anything about it. Basically, what we're going to do here is rewrite our equation. I always do that. Oh, got something on my screen there. Okay. Equals square root of 2 times mu over r plus epsilon. Okay, and if you're solving this mathematically, you would plug in numbers for mu, r, epsilon, but you're not going to do that. You're going to plug in their units kind of as if they were numbers. So what are the units of 2? I would tell you that 2 has no units. It's just the unitless integer number. So we won't even pay attention to it. Mu has units of kilometers cubed per second squared. So we'll plug that in right here. Kilometers cubed, second squared. And we'll plug in units of r, which are kilometers, below. All right, and then we'll plug in epsilon. Let's see. It has units of kilometers squared over seconds squared. Okay, so kind of just as if they were numbers in a way, or variables. Kilometers on the bottom here will cancel out one of the kilometers up here. So now we have something that's, zoom in a little bit, kilometers squared over seconds squared plus kilometers squared over seconds squared. Well, what does that mean? Well, it means that everything is kilometers squared and seconds squared. That's what we want. So what if I took the square root of kilometers over the square root of seconds squared? I would come out with units of kilometers per second. We're always going to circle our answers, kind of as a public service announcement here. In Astro, that helps our instructors, like myself, know where your thought process concluded, and we can follow your math better and give you more credit, and everything is really good in the world. Okay, number 2. So they give you an equation. It says the equation to find the power in watts needed from a solar array to power a spacecraft is shown here. Okay, this is true. We're going to actually spend a whole lesson on these concepts much later in the course. Right now, though, you don't actually need to know a darn thing about solar panels to solve this problem. All you need to do is isolate what they want, which is PSA. And what I always like to do is isolate the variable and then plug in numbers. So let's do that. I'm going to rewrite my equation down here. PSA times time and sun. I'm going to kind of just mark off the variables with parentheses. And it equals P times load in eclipse, I'm going to abbreviate that, times time in eclipse, plus P times load in sun, abbreviate that, plus times TS, top secret. No. All right, so what if I just divided both sides by TS? That would cancel out the TS there, and it would give me PSA alone, and I could plug and chug. Well, that's exactly what I'm going to do. So load in eclipse is 100 watts. Time in eclipse is 0.85 hours. plus loaded in sun is 160 times the time in the sun, which is 1.15, all divided by the time in the sun, which is 1.15. All right, calculator, come save us. Let's see, plug and chug. 160 times 1.5, boom, bum, divided by 1.5. All right, I get that this is equal to 233.91. Oops, it's supposed to be a decimal. Watts. Always box our answer. And I didn't need to know a single thing about solar panels to solve that problem. This could have been Q, this could have been X, this could have been what. Doesn't matter. I gave you letters, and I gave you what those letters stood for as far as numbers, and that's all you need to solve. So let's carry that throughout the rest of this exam here. Not exam, prep. Not prep. Review. Call it what you want. Okay. You just purchased a new digital camera that claims it can take 8 megapixel images. Ooh. You can tell this is somewhat an older review. It was developed some time ago because I think my iPhone is up to, is it 12 megapixels now? So, unless you're a photographer, does anybody buy cameras anymore apart from phones? I don't know. Anyway, it says the camera brags. Ooh, it brags that it captures high-res images up to that many pixels by that many pixels. Use your ability to cancel units to solve the following problems. Well, we're going to use unit cancellation, but mostly this is just a logic exercise. And it's actually, again, you don't have to know anything about digital cameras or telescopes in space or anything like that. First part of the question says, how many pixels in an image are there? Well, it tells us each image has kind of a short end and a long end. It kind of takes pictures, as you might expect, in a rectangle here. And the long edge, it says, is 3264, and the short edge is 2448. Pixels by pixels. So just, the same way as if this was in the area of a backyard and we were looking for square feet or square meters, we're just going to take pixels times pixels, and that'll give us how many pixels are in the image. Mm-hmm. So there are 2448 on one edge times 3264 on another edge pixels in every one image. Okay, so if I just multiply, I think that's going to give me what I want. 7990272 pixels, and we're always going to write units after our answers. Pixels per image. Well, that's what they wanted, is how many pixels in every image. So we're set there. Okay, if each pixel requires 12 bits to record the light, how many bits are in an image? So it basically is just saying, okay, you told me how many pixels are in each image, but if I'm making a hard drive, I don't really know how many bits it takes to store each pixel. So hook me up and tell me how many bits are in a pixel. And so it does. It says 12 bits in each pixel. Pixel, 12 bits. So I know how many pixels are in each image. In fact, I'll expand this out. Pixels per one image. And I know how many bits are in a pixel. So I would like to get pixels to cancel out. So that's how I'll do it. Now I have bits per image. And that's 9588364 bits per image. That's basically how big the data is of one picture. Okay. And then it says your camera came with a 256 megabyte memory card. Yikes. Again, small. Like iPhones and Androids and all that have gigabytes of storage. Even on the low end, you're getting like 16 gigabytes. But I digress. Your ancient camera came with this 256 meg memory card. How many images can you store on it? And then they remind you there's 8 bits in every byte. That's kind of a computing standard there. So a megabyte is that many bytes, they say. And that's true. And we'll figure that out. But anyway, so let's see. How many images can you store? So first of all, I know how many bits, or rather bytes per hard drive I have. Here's how many I have. What does mega mean? What's M? What does this M stand for? Well, if you see an M as a prefix, it's mega, which is 10 to the 6th. It's a million. You're going to multiply by a million. So 256 times 10 to the 6th bytes are on every memory card. I'm going to abbreviate memory card. So on this memory card, this one memory card, there's that many bytes. How many bits are there in each byte? Well, they tell us one byte is 8 bits. Okay, so 256 e to the 6th times 8 gives us 2.048 times 10 to the 9th bits per memory card. Okay, so now I know how many bits are able to be stored on this memory card, and I, from the previous problem, know how many bits are in each image. So this sounds like a job for multiplication. Bits per one memory card. And then I want to know how many images per memory card, so that means I want to get bits to cancel out. So bits on the bottom would be 9588364. Bits are in each one image. So now the bits cancel and I'm left with, images per memory card. That's awesome. So let's see what that comes out to be. 9588364. Boom. So that ends up being 21.359 images per this one memory card. Now, they might ask you, hey, what is the number of whole images, right? Because there's this 0.359 of a picture. So that'd be like a picture that's only 40% complete. Sometimes pictures have errors like this. So if we asked you for whole images, which we didn't, but if we did, that would just be 21 whole images. Cool. All right. Triangle math. I call it triangle math, but lo, it is not called that. Lo, I tell you, I say unto thee, it is called trigonometry. All right, so if you guys remember SOHCAHTOA, sine of theta equals the opposite over the hypotenuse of a triangle. The cosine of theta is adjacent over the hypotenuse, and the tangent of theta is the opposite over the adjacent. SOHCAHTOA. So there you go. So now they're going to ask us to use that math to find out what are Vx and Vy of this triangle. And they give us how big magnitude-wise the hypotenuse is, which is 12. It says what are Vx and Vy. Okay, easy day. So we know that the sine of that angle is, we'll do Vy first. So opposite over hypotenuse, which is 12. So that means Vy is, if we multiply both sides by 12, that'll cancel that out and give us Vy, trying to divide that out there, 12 sine of 30, and that is 6. All right, cool. Let's do the same thing for Vx, and so we know that the cosine of theta is Vx over 12. That would be the adjacent, right, over 12. Oh, trying to keep these separated here. So if I multiply again both sides by 12, that'll isolate Vx for me. 12 cosine of 30. That's going to equal 10.392 as the x side of the triangle. So there's Vx and there's Vy. Nice. Now it says write the vector v in standard vector form. What's that talking about? This is just saying write v in terms of how much x-ness there is and how much y-ness there is that gives us vector v-ness. So here's what that's going to look like. Vector v is some amount of vx. Well, how much vx is it? It's 10.392 times vx. We're going to put a little hat on that because it's not really multiplying by vx. 10.392 is v sub x. We're saying it's 10.392 in the v sub x direction. That's what this little hat indicates. It's a direction indicator. So v sub x hat isn't a number. It's just a direction. It's a pointer. All right, so it's that much in the x direction, and let's go back to red. And it's 6 in the v hat direction. That's the vector form that they're looking for. So there you have it. All right, we'll keep pressing here. Okay, vectors versus scalars. This is a reminder. So a vector is some magnitude of something plus a direction of something. It has both magnitude and direction. Scalars have only magnitude. No direct. Oh man. No direction. Oh, my wrist keeps hitting the thing. Direction. There we go. So it wants us to identify these quantities and say, well, which one are they, vectors or scalars? Well, no problem. So position versus distance. These are kind of two brothers, if you will, two cousins. Position is how far you are from something in a direction. So that means magnitude plus direction. That must be a vector, and it is. Distance is kind of its cousin, because it's just, hey, how far are you from something? I don't care which direction. So it's kind of like when you're on the way home with groceries and your significant other is like, how far out are you? And you're like, I'm a mile out. She or he doesn't really care which direction you are out. They're just hungry and want groceries. So distance, which is what you tell them, I'm a mile out, that's just a scalar. Because you're not saying I'm a mile south of you, you're just saying I'm a mile out. Okay. Torque. This might be a reach back to your mechanical engineering courses, but torque is a force that's acting at a distance on something. And so force, which is below, let's look at force. Force is a vector, because if you guys remember, what gives force its vectorness is the directional component of acceleration. Now you could have, and this is weird because we don't have another word for force, it could also be a scalar, but default to thinking of it as directional. You should default thinking of it as directional, which makes it a vector. And that means that if torque is force at a distance, that means, so force is a component of it, the force part's directional, and the distance part's not, right? Force at a distance, but the force part is directional, and so that makes torque a vector too, because force is a part of it. Energy, on the other hand, you can probably easily see as a scalar. So, for example, how much energy does your iPhone need to charge? Oh, it needs 10 million joules. I know it's not the right number. 10 million joules, say. And you might say, well, couldn't you have 10 million joules in the south direction? It's like, I don't know how that makes any sense. So really energy is just, it doesn't have any directional component to it. Just joules. That's what energy is talking about. Momentum, on the other hand, if you guys remember, and we'll talk about this in a little bit, is mass times velocity, which velocity, as we will see in a second, I'm going to write this as another good example. Velocity is a vector versus its cousin speed, which is a scalar. Velocity is I'm going 70 miles an hour north on I-25. Speed is, sir, do you know how fast you were going? You get pulled over, and you say, well, first of all, you say, I'm not sure. But he says, you were going 70 miles an hour, and the limit's 65, whatever. But he doesn't really care which direction you were going. You just flew by his cop car, and he pulled you over. So that's speed versus velocity. All right, so momentum has velocity as part of it. And because velocity is a vector, momentum is also a vector. A couple other, another example I can think of is mass. You could probably imagine that being a scalar, because you've never asked your buddy how heavy they are, and they say, oh, I'm 200 pounds. And you might say, are you 200 pounds northwest? And dude is like, I don't know what you mean. I'm just 200 pounds. Doesn't matter which direction. So mass is a scalar, right? Anyway, so that's kind of, remember, if there's a directional component to it, then rather it is a vector. And if there's not, it's a scalar. Okay. Magnitudes of vectors. So fresh, so clean. So this is actually a pretty easy process. What you're going to do for any of these, so let's take a vector as an example. You look at basically each component and you square it. So the I hat component squared plus the j hat component squared plus the k hat component. What? There is one. It's just not written because 1 times k hat is just k hat, but we need it down here. So you're going to add all of those once they're squared and then take the square root of whatever that ends up being. So that's 5 plus 3 plus 1. Square root of 9 is 3. Okay, well, let's try this for B. B throws in negative components, so things are a little spicier. You want to make sure you square the negative value. Don't square it and then add a negative. The order matters with that, or else you get something different. Okay, so that's 4 plus 16 plus 16, so that would be 36. Square root of that, and that is 6. All right, let's try it for arguably the most challenging one is C here, because they only write one of the components. Well, what must that mean? Well, that means that they're just 0. This vector has nothing but I hat. It has no j or k hat. So we'll just take that into account. Negative 9 squared plus 0 squared plus 0 squared. So that's the square root of 81, and that is 9. So there you have it. Square all the components, square each of them, then add those together, then take the square root of what that is. That's how you take the magnitude of a vector. Ooh, triangle. More triangles. Love it. Okay. So we're given a picture of a triangle, and then it's given to us in vector form as well. This kind of a problem is designed to help you, force you actually to realize that vector math, I was going to say vector math is hard. It's really not, though. Basically, taking the magnitude of a vector is not the same as adding the vector components. So I'll show you what I mean. Okay. C vector equals A vector plus B vector. I don't know if you guys buy that, but to get to C, if you started right here, for example, you'd need to go however much in the B direction, and then you'd have to go however much in the A direction, and that would get you to C, or basically the same position as if you started there and followed along C's path. So in vector terms, what this is talking about is, so if A is 4000i plus 0j, that's A vector. We're going to add that to B vector, which is 0i plus 3000j hat. That is B vector. All right, deal. So the rule here is you can't add j's to i's and i's to j's. You got to keep them separated. Okay. That's probably too old for you guys, but all right, so 4000i plus 0i, add that to, 0j plus 3000j. Now when we add vectors, we're going to get a vector. That's important. So this ends up being 4000i plus 3000j. That's the vector that describes C vector. Oops, I covered up my vector hat. And that kind of makes sense, right? We had to go 3000 in the J direction and then 4000 in the A direction, and that gave us the resultant vector of C vector. Okay, Now it says, well, what is the magnitude of C vector? So kind of going back to the previous problem, what did we do for that? We took each of the components of a vector, squared them, added them, and took the square root of what came out of it. Let's do the same thing for C. Thankfully, we just got the C vector. Now, as a side note, when you see a letter that's just alone, like C, that's the same as saying the absolute value or magnitude of the vector. Basically, you just write it without the vector hat because it's just a magnitude. Okay, so we're going to do what we did before. Take 3,000 squared and we'll add 4,000 squared. Nice. Some of you guys are ahead of me because this is a 3, 4, 5 triangle, so you can actually just go that direction, but this ends up being 5,000. So remember, C vector is not even the same animal as the magnitude of the C vector because we've stripped out the direction when we take the magnitude of it. It's direction agnostic. So C vector has an I component and a J component, but C absolute value or magnitude just has the magnitude, which is 5,000. So those aren't the same thing. All right, now let's do, this is also going to tell you that the absolute value of A, I keep saying absolute value, the magnitude of A plus magnitude of B, which is rewritten, just remember, as letter plus letter without any adornments, is adornings? Whatever, without any decoration. What's that going to be? Okay, well, absolute value of A would be square root of 4,000, let's zoom in, 4,000 squared plus 0 squared, and then add that to the absolute value or magnitude, of B, which is 0 squared plus 3,000 squared. So that ends up being 4,000 plus 3,000. Remember, once we take a magnitude, we strip out the direction, so it doesn't matter the direction. Magnitude of A plus the magnitude of B is 7,000. That is not the same as 5,000. And that's what we force you to do here in D. Just take a look at A plus B. So what was A plus B? This was 7,000. C, magnitude of C, we found was 5,000. Alligator eats the bigger number. So circling the correct operator, that's the alligator or the equal sign. Those are the operators you have to choose from. Not like a space operator. That's a different kind of operator. But A plus B is different than C, different value. So that's what we wanted you to get out of that. All right, keep pressing here. Oh, yes. Okay. Dots and cross products. Use the following vectors to answer the questions below. And they give us several vectors, and they give us a constant row. We'll get to that in a little bit. Okay, how do I do a dot product? Well, first thing I want to tell you is let's look at A and use it as a case study. Problem A, I mean. Dot products produce scalars, always. So that means you're going to start off with two vectors and come out with something that has no direction. So let's do that. Here's how you do a dot product. I rewrite the two vectors in question on top of each other. And I draw a line underneath like I'm subtracting them, but I'm not. I'm not going to do that. What I'm going to do is I'm going to take each of these components and multiply them. Multiply? Wow, multiply them. 1 times negative 2. Okay, multiply the i's. Now multiply the j's. Multiply the k's. So 2 times 4. 3 times negative 6. So I took the I components, I multiplied them. I took the j components, I multiplied them. I took the k components and multiplied them. Why am I saying that? Multiply. I may as well just keep saying it. Anyway, after you've multiplied each of those, you're going to add those quantities. and see what that number comes out to be. So you'll have negative 2 plus 8 minus 18. It ends up being, I believe, negative 12. Negative 12 in which direction, Major C? No direction, right? Because dot products make scalars. Cannot emphasize this enough. There's great confusion on this. Okay, so now let me draw a line and kind of separate out my space for, oops, draw it under that. There we go. A dotted with B. That's what we just did. Neat. I left myself some space here because cross products take just a little more space. So all of this will be cross product space. Let's do it in green. Oh, yeah. All right. Cross products have a couple of rules. Order matters. And they produce vectors. So unlike the dot product, what's going to come out of a cross product is another vector. You start off with two vectors, get another vector. And what it is the right-hand resultant rule, basically. Remember right-hand rule from EE or physics? You have two vectors. The right-hand rule gives you that third vector. So, yeah, it's essentially mathematically finding out what that third vector is through this process. Dot products are kind of like a shadow, if you will. Dot products are like, what's the shadow of A onto B if you were to, like, if A and B were two vectors and the sun was above them, how much of A would shadow down onto B, basically. But, yep, cross products are, hey, man, I need to find that third vector that is part of the right-hand rule, three-dimensional of two other vectors. So here we go. Here's how I do it. It's something similar to what we did before, where I start off by writing the vectors on top of each other. And again, order matters here, so don't forget that. What was A? There it is. 1I hat plus 2J hat plus 3K hat. And C is negative 3I plus 0J plus 4K. Okay. Now, I don't do the same thing as the dot product. I'm not going to draw that line, not going to multiply those components. It's a little more complex than that. I'm going to use those vectors to build a matrix. Are you ready, Neo? Are you ready to see the matrix? Do you want to know what it is? In this case, we're taking the green pill, I guess because my Apple Pencil is coloring in green right now. Anyway, write I, J, and K, just the letters, and then you're going to write the components of each of these vectors on top of each other. So A is 1I, 2J, and 3K. C is negative 3I, 0J, 4K. Ooh, 4K. 4K high res. Nice. I guess that doesn't even count as high res anymore, does it? Yeah, so we built that matrix, and here's what we're going to do. You're going to have to imagine, if you will, putting your hand over the I component, and then we're going to work with it. But basically, what I should do is back up a little bit. I'm going to write a little frame, basically, for my answer. Because remember, two vectors crossed will give me another vector. So I'll have something blah in the I direction, some blah in the J direction, some blah in the K direction. That's just how vectors go. And so I'll take each component in turn as I cross them, and you'll see what I mean by that. As I cross them, and then I will put them into the frame kind of one by one. Okay, so in fact, I want to do one more thing. A weird property of cross products, it's just how they are, is the J component. You have to throw an extra negative sign outside to play with. That's just how it goes. Okay, so I cover up the I hat column, and then I work with J and K. So thinking about what I want to get out of my I hat component, sorry, let me rephrase that. Let's work with the I hat component. Cover it up. What you're going to do is you're going to start with the upper left of the j component column, and you're going to multiply by the k hat component, lower k hat component, and that's one part of it. And then you take the lower j times the upper k. Ta-da, there's the cross. That's why we call it a cross product. So now let's write that out. 2, 4, minus, the insides are always minus, insides of the brackets, 0 times 3. All right, cool. We're going to repeat that process for each of the components. Seriously, that's simple. So cover up j and just work with the I and k columns. So that'll mean we're going to multiply upper I times bottom k times lower I times upper k. Not multiply them, multiply then add. You know what I mean. I'll show you what I mean. I'll tell you what I mean, what I really mean. 1 times 4 minus negative 3 times 3. Of course, not forgetting there's an extra negative sign out front we're going to have to deal with. All right, cool. And then k hat. So, sorry, brain froze because I need to get rid of those crosses. Now cover up the k hat column and work with I and j. So just like I did before, I'll draw it out. Upper I times bottom j minus bottom I times upper j. There we go. 1 times 0 minus negative 3 times 2. Sweet. We definitely have this ready to go now. Let's simplify. Okay, I'm going to rewrite my my frame here. I, j, and k, and of course, not forgetting that j has an extra negative out front. That's just how it is. That's how this process works. So, okay, 8 minus, let's take the I hat component. 8 minus 0. It's going to be 8. 4, let's here, I'll write this one out. 8 minus, I'll write them all out. 4 minus 9, that's going to be 13. But then there's an extra negative, so it'll be negative 13. But we have 0 minus a minus 6. Okay, so let's simplify even more. I like to make my negative sign out here purple so it stands out because it's easy to forget. All right, so we have 8. 4 minus a minus 9 is 13 because that means 4 plus 9. And then 0 minus a minus 6 is plus 6. So I'm going to rewrite it horizontally. A crossed with C gives us a vector that is 8I minus 13J plus 6K. There you go. Now, that was A crossed with C. I guess I can draw my line a little bit higher. That's A crossed with C. Sweet. Okay, so last thing here is just multiplying a constant by a vector. And this is easy money. I want you guys to just get this as far as getting those points. It says rho. Up here it says that rho is 2.0. Rho 2.0. And it says multiply that by the d vector, which is negative 2i. Let's see, I'll write it out. D equals negative 2i plus, oh man, it doesn't say a number next to j. That must mean it's 1j. And if I didn't write it at all, that means there's a 0 next to it, so 0k. So multiplying a constant by a vector basically is like take the constant, multiply it by the I hat, then take it, multiply it by the j hat, multiply it by the k hat. Now this is just multiplying a scalar times a vector. It's making a vector bigger, but it's still a vector. So here's what I mean. 2 times negative 2i is negative 4i. 2 times 1 is 2 for j. And then 2 times 0 is 0 for k. So like I said, still have a vector, just a bigger vector. All right. Now, what I'm going to tell you here, and I want you guys to actually work this through and prove it to yourself. But A dotted with B is the same value, the same scalar, as B dotted with A. And we found that that was negative 12. I challenge you to prove that to yourself. However, comma, A crossed with C is not the same as C crossed with A. Having solved this before, I can tell you, just happens to be C crossed with A is negative 8I plus 13J minus 6K. So it's essentially all of the signs are reversed because A crossed with C, here, you know what, I'll write it in green because that's when we did it above in green. Because A crossed with C, like we just found out recently, was 8I minus 13J plus 6K. So those two are not the same. A crossed with C and C crossed with A. The signs are all flipped. So you can take that to the bank. Dot products are happily equal to each other. Cross products are angrily, you might imagine, like the Brits say, they're cross. They're cross with each other. A cross with C is not the same as C cross with A. Well, it sounds a bit Australian, doesn't it? Yeah, sorry. They all get mixed up, don't they? All the accents. Okay, so having said that, we can say here that A dotted with B, B dotted with A, that's a true statement. A crossed with C, not equal to C crossed with A. That's a false statement. Cool. All right. Last page. Here we go. Get up for it. Okay, find the value of x and y using the following equations given A equals 5 and B equals 25. I'm going to write that over here. Give myself a break. Okay. Natural logs and logs kind of have the same operation. So basically what we want to know in these equations is if you're given, or if you have an x, what's x, and if you have a y, what's y. Okay, so in this first one, let's just take A, parenthesis. We want to find x. Well, x is trapped inside this ln, this ln, which stands for a natural log. It's a natural log function. How do I isolate that? How do I get rid of that ln function, if you will? Well, the way I do that is I raise both sides to the constant e. So I'll take e to the b, and I'll set the equal to e to the ln of x, natural log of x. Here's what that looks like. E to the b equals e to the natural log of x. E to the natural log of something gives you the something. It kind of cancels out. It doesn't kind of cancel out. It definitely cancels out. So that leaves us with e to the b equals x. Well, what was b? It's 25. We're given a constant. E to the 25th. Oh my stars, that's a big number. Okay, it ends up being 7.2 times 10 to the, let's see, 10th. And no units were given, so we don't have any units to give back. That's what x is in that equation, given b is a constant of 25. Okay, let's see if the next problem is just as straightforward. I bet you it is. We want to find y. It says it's equal to the natural log of a constant over a constant, which we were given. A and b, we know. 5 over 25? Plug that in your calculator and get those free points. Comes up to negative 1.609. Sweet. I wonder if the next problem will make us pay for the ease of the previous two problems. Turns out, yes, it will. This one's a little more complex, but not to fear, not much. Let's take the e to the of both sides here. Take the e to the. So what do I mean by that? Well, e to the a equals e to the natural log of b over b minus x. That gives us a cancellation there. This is just going to be kind of a multi-step, meticulous process. We're just going to keep simplifying until we find and isolate x. First, we want to isolate it, so stick with letters. Don't plug anything in just yet. Okay, so at least we got rid of the natural log function. One challenge completed. Now we still have x in kind of a perilous situation because it's next to a constant and in the denominator of a fraction. So, okay, there's a couple things we could do. Let's multiply both sides by b minus x. So that'll cancel out over there and get it out of the denominator. I like that as an idea. That's good. So what's that going to give us? I'll just keep marching here. It's going to give us this b minus x term times e to the a equals b. Well, now b minus x is trapped. Well, b minus x is not as trapped as before. It's not in a fraction anymore, so that's good. So what now? Well, I'm going to multiply through e to the a times both of these components. So we'll go down this way. So that'll end up with e to the a times b minus x times e to the a equaling b. Okay, well now I just have x with one term. So if I can, man, in one move almost I can do this. So what I'm going to do, I'm just going to actually subtract e to the a b from both sides. So that'll give me negative x e to the a equals b minus e to the a b. Now we're almost there. I'm going to divide both sides by negative e to the a, and that'll isolate x for me. Finally. So x is b minus e to the ab, so 25 minus e to the 5 times 25 over negative e to the 5. Now all that's left is to plug and chug and see what we get. And to make sure that we honor a calculator, especially if you're using the honor later, you've got to make sure that your parentheses are all in the right place, or else things will come out a little wonky. Okay, and after all said and done, and this is correct, I get 24.832. Sweet. So what do we do? Well, basically we just kind of reminded ourselves of how logs work. If I have something that's equal to e to the something, I take the natural log of both sides. Or if I have something that's natural log, I take the e to the of both sides. Raise both sides to the power of e. Power of e. That's kind of what I think of. And that's very powerful. Okay. We're just about there. Linear momentum, they tell us, can be expressed as p vector, where p vector is equal to m mass times velocity vector. Cool. Like we said above, momentum is a vector. So in this case, that's not going to really make a difference. But using this equation, how fast, and they give us a units to shoot for. In kilometers per second, would a 3 kilogram piece of space junk have to be traveling in order for it to have the same linear momentum as a 25 kilogram Mack truck traveling 100 kilometers per hour? Mack is a brand of big semi-tractor trailer truck. So this is the kind of thing that would haul a semi. So basically, if you had a Mack truck going down I-25 at like 65 miles an hour, which is like 100-ish kilometers per hour, how fast would this little space junk have to be going to hit you with the same impact? Well, let's see. What they're telling us is, hey, assume that the two momentums are equal, right? It says same linear momentum. So we can set I'm going to call it velocity of the junk, or momentum of the junk, rather, P sub j, equal to the P of the truck. And that means if I plug in what the equation is, I can go mass of the junk times velocity of the junk and set that equal to the mass of the truck times the velocity of the truck. What I really want to know is velocity of the junk. That's what they're asking us for. How fast does the junk have to go? So what if I divided by both sides by mass of the junk? That would probably give us what we want. So this will equal 25 kilograms times 100 kilometers per hour over mass of the junk, which is 3 kilograms. I do believe that gives us a huge amount of kilometers per hour. But P.S. space junk often does travel very, very fast. So, however, is this kilometers per second? No, it is not. They want it in kilometers per second, so don't stop here. Let's take a page out of the book we were... take a page out of our previous book above where we were doing unit conversions. Kilometers per hour. Let's get kilometers per second. Okay, so in 1 hour, I want hours to cancel. There's 60 minutes. And in 1 minute, there's 60 seconds. The hours cancel out, the minutes cancel out. Now I have kilometers per second. Oh gosh, I'm running out of space. No pun intended. This gives us a speed of 23,148 kilometers per second. So again, 83,000 odd kilometers per hour. That's correct. But it's not what the problem asked for. It wanted it in kilometers per second. So pay attention to that. It's in bold and underlined, so it matters. It matters a lot. Okay. Pressing on. All right, this is the last of the review set problems here. Find all of the angles between the following vectors. Drawing a picture may help. I always think drawing a picture will help. So, for example, let's say B is this vector here. I'm not sure if this is what it looks like, but we're just going to use this as a teaching tool. Okay, A and B. And I say to you, I give you this equation here, A dotted with B is equal to magnitude A, magnitude B times cosine theta. And I say find all the angles. Well, you might say, well, here's one angle definitely between, A and B. That makes sense, right? That's intuitive. But what's not so intuitive is the other angle between A and B, which is basically the rest of the circle all the way around, if you think about it like that. So let's say this angle here is theta. We'll call it theta 1. Let's say it's, 30 degrees. Theta 2 here would be equal to 360 minus theta 1, and that'd be 330. Okay, so I don't know if those are the values, so I'm going to erase these for right meow. And we'll just say we want to find theta 1, and then we're going to find theta 2, which is going to be 360 minus theta 1. We can take that to the bank. Okay. Now, a couple of steps are involved in this process. First, it says A dotted with B is equal to AB cosine theta. It says find both angles. So we want theta alone. That means I need to find what A dotted with B is and magnitude of A times magnitude of B. Well, let's start off one thing at a time. A dotted with B. I'm just going to use the fact that they're written on top of each other already. I want to make sure I add in my ghost K hat because it's not written. That means there's a 0 in front of it. 3 times 3 plus 4 times 4 plus 5 times 0. And that's going to equal 9 plus 16. And that equals 25. That's A dotted with B. All right, that's the first thing we need to know. So 25 is what that value is. Now, what's magnitude of A and magnitude of B? Well, magnitude of A is the same as writing that. And that is, if you guys remember from above, square all the components, add them, take the square root of what comes out of that. Okay, so let's see, 9 plus 16 plus 25, square root of that, 7.071. Okay, same thing for B. Three squared plus 4 squared plus 0 squared. That gives us 5 because that's square root of 9 plus 16, which is 25. Square root of that is, of course, 5. As I double check myself. So that's the magnitude of A and the, why did I do that? Magnitude of A, magnitude of B. Okay, Now we have everything we need, I argue. Here, I'll do this in red. This is the next kind of step. I guess there's a few steps. You have dot product here. You have the magnitude equations down here. And then the last step is just kind of solving this equation. So A dotted with B equals magnitude A, magnitude B times cosine of theta. Well, I tell you what, why don't we divide both sides by A times B so that we can at least get cosine theta alone. Cosine theta is A dotted with B over magnitude A times magnitude B. Well, what's A dotted with B? We found that it's 25. And what's A times B? Well, that's 7.071 times 5. Last thing we need to do is, that's nice, but we got to isolate theta. So take the inverse cosine of both sides, and that'll give us inverse cosine of A dotted with B over AB. Okay, so that equals, oh, you know what? Here. Oh, that's fine. Okay, inverse cosine of A dotted with B, which we found out to be 25, over A, which is 7.071 times 5. Ooh, ran out of space almost. Make sure your calculator's in degrees. So let's see, 7.07. Wow, no, 71 times 5. Inverse cosine of that comes out to be exactly 45 degrees. Winner, winner, chicken dinner. Remember, this is just theta 1. So we found theta 1 to be 45 degrees. We still have to find theta 2. All right, so we not only found the small angle between them, but we found the large angle around the outside. There you go. Looking forward to see you guys soon. It's been a pleasure.